All right, today we're going to build a toolkit, but for your brain. This is basically your study guide to the core architectures that are powering all of modern AI. We're going to hit the landmark papers, the key concepts you absolutely have to know to really get what's going on in this field. So let's just dive right in.
So here's our game plan. We've got 4 parts. First, we'll lay the foundations. How do these models even begin to understand our world? Then we'll get into the revolution, the breakthroughs in scaling that made these giant models even possible. After that, we'll look at the application layer. How do we turn these things from cool models into reliable tools? And we'll wrap it all up with a core reading list so you can go even deeper on your own.
Okay, first up, foundations. Before an AI can write a sonnet or paint a picture, it has to learn the language of our world. And for a machine, that language is all about numbers. This first part is all about that translation, how we take messy human ideas and turn them into a format that a model can actually work with. And the absolute key to that translation is a concept called embeddings. Now, you might have heard of older methods like one-hot encoding, which is basically a giant checklist that just says if a word is there or not. It's super inefficient. Embeddings are different. They create these rich, dense lists of numbers, we call them vectors, that capture the meaning of a word. You can think of it like giving every single word a coordinate in this massive meaning space, where words like king and queen or walking and running are actually located close to each other. But here's the thing. A word's meaning can totally change depending on the context, right? This was a huge problem for a long time, and the groundbreaking BERT model basically solved it with a really simple but incredibly powerful recipe for understanding a word's role inside a complete sentence. So here's that BERT recipe. It's brilliant. It just combines 3 key pieces of information. First, you have the token embedding, which asks, what is this specific word? Then you add the segment embedding, which answers, which sentence is this word in? And finally, you add the position embedding, which tracks, where is it in the sentence? By just adding these 3 vectors up, BERT creates this incredibly rich, context-aware understanding for every single token. Okay, another super powerful way for models to learn is something called contrastive learning. The SimCLR paper really put this on the map. The idea is so intuitive. You teach a model what things are by showing it what they're similar to and what they're different from. It learns to pull representations of positive pairs, like 2 slightly different pictures of the same dog, closer together, while at the same time pushing negative pairs, like a dog and a cat, farther apart. It is a fantastic way to learn amazing features from data without any human labels at all. So we know how models can learn, but today's models are just enormous. So this section is all about the clever engineering hacks and breakthroughs that made them efficient enough that we can actually build and use them without, needing a power plant for every model. So one of the first big problems we hit was with fine-tuning. Let's say you take a giant pre-trained model and you want to teach it a new skill, like summarizing legal documents. The old way was to tweak all 175 billion parameters and then save a whole new 175 billion parameter model for every single task. It was just a complete nightmare, slow, crazy expensive, and not at all scalable. And the solution that really took off is a technique called LoRA, which stands for low rank adaptation. Think of it this way. Instead of rewriting an entire textbook for every new subject, LoRA freezes that huge original model and just trains a tiny, tiny set of new weights, these little adapter matrices. It's like adding a few super smart sticky notes to the textbook instead of reprinting the whole thing. And the impact of this is it's staggering. When you use LoRA on a huge model like GPT-3, you end up training only about 0.01% of the total parameters. Yeah. 0.01%. The efficiency gain is almost hard to wrap your head around. So let's just break down those benefits. Compared to full fine-tuning, LoRA absolutely slashes your cost and your training time. For storage, you're not saving these gigantic model checkpoints anymore, just these teeny tiny adapter weights. And this makes serving multiple custom models way easier. You just have one big base model loaded up, and you can swap these little LoRA adapters in and out on the fly for each user. All right, the next efficiency hack tackles a hardware problem. The self-attention mechanism, the heart of the transformer, it's often bottlenecked not by how fast the chip can do math, but by memory speed. So imagine your super fast on-chip SRAM is a tiny little cutting board, but your much bigger, much slower HBM memory is the fridge. Standard attention is like a chef who runs back and forth to the fridge for every single ingredient, one by one. The travel time is what kills you.
So the solution is flash attention. Instead of our chef making endless trips to that slow fridge, flash attention brings whole blocks of ingredients over to the fast cutting board all at once and does as many calculations as possible before writing the final result back. It uses these really clever techniques like tiling and recomputation to just dramatically cut down on that memory traffic, making it up to 3 times faster while, and this is key, producing the exact same mathematical result.
But hey, while flash attention makes transformers faster, what if we could just change the architecture completely? This chart here shows the incredible promise of something new called state space models, and specifically the Mamba architecture. Now, unlike transformers, which have to look at the entire sequence all at once, which makes them scale quadratically, Mamba processes information in order, sequentially. This lets it scale linearly. And the result? It can achieve an incredible 5x higher inference throughput. This could be a total game changer for working with really, really long sequences. Okay, so we've got these incredibly powerful, super efficient models. But how do we make them reliable? How do we make them useful in the real world and, stop them from just making stuff up? That's what this next section is all about. So one of the biggest problems with large language models is that they tend to hallucinate. They just make things up. A really powerful solution is called Retrieval Augmented Generation, or RAG. And this quote is the absolute perfect analogy for it. With RAG, you're not asking the model to just remember some fact from its training data. You're giving it an open book exam. You're asking it to build an answer based only on the documents you provide it, right now.
Here's how that works in practice. A user asks a question. The system first goes and retrieves relevant documents from some knowledge base, say your company's internal wiki. Then it literally stuffs that information into the prompt, right there with the original question. And then it asks the LLM to generate an answer based on that specific context. And this is so important, to cite its sources.
This whole RAG process makes AI systems so much more trustworthy. It drastically reduces hallucinations, it lets the model use up-to-the-minute or private data it was never trained on, and it provides citations so that users can actually go and verify the answers for themselves. This is how you build trust. Finally, to make a model truly useful, you have to know how to talk to it. And I mean it. Prompt engineering is a real skill. This slide shows the 7 key ingredients for a great prompt. If you can clearly define the persona, the instruction, the context, the output format, the target audience, the desired tone, and any input data, well, you can get incredible control over the model's output and get exactly what you want. Whew! Okay, we have covered a ton of ground, from embeddings and efficiency all the way to real-world applications. So now, let's just pull it all together into the syllabus for the study guide, the core papers you can read to really go deeper on all this stuff.
And here they are, the foundational papers for basically everything we've just discussed. You've got BERT for that deep contextual understanding, SimCLR for learning without labels, LoRA for efficient fine-tuning, flash attention and Mamba for making things scale, and RAG for building tools you can actually trust. These are, quite literally, the blueprints of modern AI.
So that's our tour of the modern AI toolkit. Every single one of these innovations solved a problem that, at one point, seemed nearly impossible. Which, of course, leaves us with a final question. What is the next impossible bottleneck? What's the fundamental limit that researchers are trying to smash through right now? Because that's where the next wave of breakthroughs is going to come from.